thank you all for coming to the talk, Plasma, the Mysterious Fourth State of Matter. So what I'm going to be talking about today is, first of all, what a plasma is. Then I'm going to show you all some examples of plasmas, and some of them might surprise you. And then I'm going to talk about the research that people are doing on plasmas now. And actually, I'll touch on the research that I'm doing at Imperial College London in the plasma physics group. And if you haven't noticed, my name is Arthur Turrell. Okay, and I'm studying for a PhD in plasma physics at Imperial College London. So I've used this word mysterious, and you're probably thinking, well, that's actually a bit of a dramatic word to use. But actually, plasmas are mysterious because we don't come across them very often. Most of the states of matter that we see, we understand them, we see them often, we know how they'll behave when we do things to them. But plasmas are really strange and different. And actually, researchers have a problem with plasmas because they are so different. We're never sure how they're actually going to behave. So I'm going to try and keep this talk as simple as possible, because I want all of you to understand as much as possible. I want to keep you all on board. But there will be time for some questions at the end. So if there is anything that you didn't understand or you thought was wrong or anything you want to comment on, then if you just wait to the end and we can have a chat about those things then. So, I said the mysterious fourth state of matter, and some of you might already be thinking, well actually, what's matter? Well, matter is just stuff. So this table is made out of matter, this lectern's made out of matter, the whole room's made out of matter. I'm made out of matter, you're made out of matter, your grand's made out of matter, almost everything that we see is made out of matter. But what's matter made out of? Well, matter is made out of tiny, tiny things called atoms. You might have heard of these, but I'm just going to go over them and remind you about what atoms are. The first thing to say is that atoms are really, really small, really tiny, incomprehensibly small, which means that you don't have to have very much stuff to fit a lot of atoms in. So for instance, in me, now I might not look that big, there is an enormous number of atoms. And it's a number so big that there isn't even a word for it. So I'm not going to try and say it, because it's too long. I'm just going to show you. So here we go. That's the number of atoms in me. And I'm not that big. I like to think so anyway. And it might surprise you, but there's roughly the same number of atoms in you as well. And you can see why I didn't want to pronounce that number. It's so ridiculous it would be foolish to try. So in science, we often come across these big numbers, and it's quite difficult to get a grip on them because they're just too big to really imagine. So one way to understand how big they are is to split them up somehow. So what about if I took all of the atoms in my body and I split them up between every single person on Earth? So there's roughly about 7 billion on the planet at the moment. So what if I split myself up, would be quite painful for me, and gave out all of my atoms to all of those people? How many would they get? Well, it's still a ridiculous number. There is a name for this number. It's called a quintillion. It's a bit of a silly name because it's a bit of a silly number, really. And it's still, I can't really understand this number. It's just far too big. So let's see if I can split myself up even more. My poor body's already been split up between all of the people on Earth, but I'm going to put all my atoms back together, and then I'm going to split them up between every star in the universe. So those aren't just the stars in our galaxy, the Milky Way, but the stars in every galaxy, in every universe. Let's see how many atoms each one will get. It's still quite a lot. It's a more sensible number, 100,000, okay, but it's still an awful lot of atoms. So there are a lot of atoms around, and they're really, really small, okay? Right, well let's have a look at an atom. So here we have the atom. Now this is a bit of a simplified model, but for what we're talking about today, then this is the kind of model that we need. So you can see that there's a few different bits in the atom. So we've got these electrons, which are smaller, whizzing around the outside, and then in the middle we've got some bigger bits, and we just lump those all together and call them the nucleus. So the bit in the middle, nucleus, electrons whizzing around the outside. Okay, so that's our atom. Now, atoms are actually really, really interesting, and there's far too much to talk about with regards to atoms than we can get through today. We'd be here all week or all month, and I'm sure you don't want to listen to me talk about atoms for a month. So, we're just going to talk about the most important thing about atoms. And the most important thing for understanding plasmas is the fact that atoms have charged particles inside them. So you might not have heard of charge before, or maybe you have, but let's just try and understand it. So if you imagine you have colour, you have choices. You could have blue or red. Well, charge is a property a bit like colour. You can have positive or negative. It only comes in two varieties, positive or negative. In the atom, the bit in the middle, the nucleus, is positive. And the electrons whizzing around the outside, they're negative. So those are the charges in the atom. Now you might be wondering, well, why do these atoms stay together? Why do the negative electrons want to whiz around the positive middle bit? Well, it's because charges follow simple rules. And we're going to talk about these rules now. And it's these rules that keep the atom together. So, if I have, to pretend my fist is a negative electron, and this other fist is a negative electron, if I pull them close to each other, they don't really like it, and they repel, and they force each other away. And if I get two positive particles, they also push each other away. But if I get a positive and a negative, then they're attracted to each other. And this is how charges work. And this is why our atom stays together, because there's an attraction between the positive bit in the middle and the negative bits around the outside. And we give a name to this force. It's called electromagnetism, or the electromagnetic force. And I know that's a big, scary word, but just bear with me, because it's really, really important. So the electro comes from the fact that these are electric charges. And the magnetic comes from the fact that it's the same force that acts on magnets. So if you take two magnets and you put the north poles next to each other, you'll find that they don't want to go together and they repel. But if you take the north pole and the south pole together, then they attract. And it's the same force, electromagnetism. Now, perhaps you haven't really heard of electromagnetism. The force that you're more comfortable with, and the one that's keeping you all in your seats, is gravity. And we know much more about gravity, and it's got better PR people, and you don't hear so much about electromagnetism. But you might be surprised to hear that actually electromagnetism's really behind all of the states of matter that we see. Okay? But I want to ask you a question first. Which do you think is stronger? Electromagnetism, which we don't really hear about, or gravity, which keeps us all anchored to the Earth? So, everyone who thinks that it's gravity, I want you to be suddenly pulled down to the Earth by the force of gravity. And anyone who thinks it's electromagnetism, I want your hands to be repulsed by your body, because they've got the same charge, and your hands go up in the air. So, everyone who believes it's gravity, get pulled down. Okay, we've got one. Oh, we've got one up here as well. Okay, so the rest of you are physicists, aren't you? Because you know the answer. You know that it's going to be electromagnetism. Okay, well, I've got a little demo to demonstrate why electromagnetism, or at least show you that electromagnetism is much stronger. So I've got this paperclip here, it doesn't look much, and if I hold it out in midair, you'll notice that it doesn't float. It just falls down. Well, that's because gravity is pulling on it. So I've also got a magnet here, so we're going to have a tug of war between gravity below us and the magnet. Okay, so let's see who wins. I think you've probably all guessed already. But if I take this magnet down here, well, it has absolutely no problem grabbing the paperclip. But let's just think about that. There's a whole planet pulling on this paperclip. The combined mass of the Earth is pulling this paperclip down. And yet, all I've got for electromagnetism is this tiny magnet. So this tells us that electromagnetism is many, many, many times stronger than gravity. Okay, well, that sort of showed you the electromagnetic force again, because the reason the paperclip stuck to the magnet was because of the electromagnetic force. So we see that the electromagnetic force isn't just acting on the scale of atoms, but it also acts on larger scales. And I've got another demo to demonstrate that now. So, I've got a strange request. I need a volunteer, but I need a volunteer. I can see some people looking away already. Okay, I need a volunteer with big hair. Does anyone? I can see someone pushing someone else forward there. Would you mind being a volunteer? Okay, I feel like you've been pushed into it, so come down to the front. Okay, I've got a balloon now, and I'm very sorry, but I'm going to ask you to mess up your hair slightly by rubbing this balloon just on one spot here on your hair, okay? And I promise you this isn't a trick or a joke or anything. There is a good reason. Okay. sorry, what was your name? Sophia. So Sophia's going to rub the balloon on her hair, and we're going to see what happens. And basically, this is to illustrate that the electromagnetic force doesn't just act on small things, again, it also acts on large things. So if you could rub that against your hair, Sophia, give it a good rub. Now hopefully this will work. You've probably seen it before. That looks good. Okay, well let's see if we can... Oh no, have another go. We'll see if we can get it to work. It doesn't always work, this. Thank you very much. Well, there you go. Physics always works. Thank you very much, Sophia. You can sit down. Okay, so, well, that didn't quite work, but I promise you it does work. If you persist long enough and have big enough hair, eventually it will work. So what would have happened if it had worked was that some of the electrons from Sophia's hair would have jumped onto the balloon when she was rubbing her head with it, and would have given the balloon a bit of a negative charge. And then when you hold the balloon close to the wall, that brings positive charges in the wall to the surface, and you get an electromagnetic force between them. So it's the electromagnetic force that makes balloons stick to walls. Well, I've just got one other thing to show you with the electromagnetic force, because you might not know this, but electromagnetic forces are also responsible for friction. Like when you're driving down the road and you use your brakes, that's friction. Or when you touch surfaces and they feel rough or smooth, that's actually electromagnetism at the most basic level that's going on there. So I've got here a very, very scientific and technical demonstration, and this is 2 yellow pages that have been woven together, okay? So got page after page after page, and they alternate between the 2 books. And basically what happens is that there are small charge imbalances in the pages in here, and when we put the pages next to each other, the slight imbalances in charge create friction, and multiplied over many pages, it's actually quite strong. So I need a strong volunteer to have a go at this one. We've got any strong volunteers? No? You're all weak things.
Very weak.
How about you, sir? Oh, sorry, no. Okay, so what we need to do is try and separate these out. So if you hold on to the bindings and pull, this is just, there's no clue here, it's just interleaved. Okay, thank you very much. Could you pass this around and then you can all have a go? You can see that, not planted a stooge or anything. This is a real effect, so I'll start with you, and if you could just pass it around and have a go. Now don't undo the pages, because that took me a very long time. Okay. So we found out that matter was actually made out of atoms, and we said that those atoms were kept together because the charges in them, the negative electrons and the positive nucleus in the middle, felt the electromagnetic force, and that kept it all squeezed together. We also found out that electromagnetism is actually quite strong. Well, what we're going to see now is that those familiar states of matter, like solid, are actually a result of the electromagnetic force. So I'm going to need about 6 volunteers for this. Okay. I can see 2 possible ones here looking excited. Yeah, you're nodding. Okay. We have some more volunteers. Yeah. Okay. Come up. Can we have about 4 more people? We can see 2 lads up. Yeah. Come down. Yeah. Come down. 2 lads up there. If you want to come and join, that's great. No. Okay. Well, you don't have to come. Okay. So this is a solid, and this is a classic example of a solid. This is actually salt, or sodium chloride. This is a very regular solid, but solids aren't always as regular as this. But what I'm going to do is I'm going to ask our wonderful volunteers if they would be a solid, and they would feel the electromagnetic force keeping them in place. So the rules of a solid for our volunteers are that solids have to stay fixed, and they have strong bonds to their neighbours. So if you can all make strong bonds to your neighbours by grabbing onto them. So if you both grab each other's arm, that's it. Okay. And now you have to stay fixed to the spot, but move as much as you want, as long as you hold on to your neighbours. Okay, so you can wiggle about, but you have to stay fixed to the spot. Okay?
Oh no!
Okay, great. Thanks, volunteer. Okay, I'm going to ask you to just stay there for a second, because we're going to use you again. But thank you for being a wonderful solid. Okay, so solids have very strong electromagnetic bonds between the atoms. But what happens if we take a solid like ice and we start turning up the temperature? Well, if we turn up the temperature, there's more energy around for the atoms to vibrate and move. And actually this energy goes into conquering the electromagnetic forces that are keeping them together. So if I heat up my solid, I'm going to get a liquid. Okay, well volunteers, if you're happy, would you like to now be a liquid as I turn the heat up? So the rules of liquids are that you can move around, but you must always have some part of you touching one of your neighbours, okay? Because there are still bonds between the atoms in a fluid, so you must stay touching, but you can move around freely, okay? Apart from that rule. So that's it. You can swap neighbours, you can go forwards and backwards as long as you're touching. You have to be touching at least your nearest neighbour, but it doesn't matter who that neighbour is. You can switch around. Okay, very, very good fluid volunteers. Thank you very much. That's excellent. Okay, so we've got a liquid. What happens if we turn up the heat some more? Well, you probably all know the answer, really. We're going to get a gas. And gases are quite different again. And okay, final state of matter, volunteers. Don't worry, I'm not going to ask you to do a plasma. I'm going to ask you to be a gas. So gases actually, they don't really care what their neighbours are doing, and they don't feel those strong electromagnetic bonds to their nearest neighbours. They're just happy to go on in straight lines until they hit another gas molecule or they bump into a wall. So if you could all now be gas molecules and just go about your business, and you don't care unless you hit something else. Okay, brilliant. Could you all give that? So we're all familiar with those states of matter. We've all seen solids, liquids, and gases. And it sort of seems like actually we've conquered the electromagnetic force now, because the particles in the gas, well, they could just carry on about their business. They didn't care what any of the other particles were doing. But actually, that's not quite true, because if we turn up the heat some more, we're going to get something else. We're going to get a plasma. But what actually is a plasma? Where's that extra energy going? It seems like we'd already conquered the electromagnetic force. So what's going to happen? Well, we need to go back to our atom to understand what's going to happen. So here's our atom. And actually, before when we put energy in it, it meant that atoms could move about more freely. But now when we put energy in, it means that our atom's actually going to split up. So we're going to get the positive nucleus and the negative electrons, but actually they're not going to be attached anymore. They can go around differently, they can go around separately if they want to, because we put enough energy in to conquer the electromagnetic force that's holding the atoms together. Okay, so what we end up with is, instead of having nice neat atoms, we end up with a big sort of sea or net of positive nuclei, or ions is what we call them, and negative electrons. And that's what a plasma is actually made of. So we know what a plasma is made of, but we're still not really any closer to understanding how they behave. For instance, we don't know if they flow like a liquid, or if they follow straight lines like the particles in our gas did. We don't even know if they've got the strong attraction between them, between the particles, like in a solid, although we might suspect they do, because you can see that they're charged, and we know that the electromagnetic force is quite strong. So we're going to answer the questions about how plasmas behave soon, but I thought it'd be nice first to actually stop talking about plasmas and actually just see some. So we're going to see some next, but first of all I wanted to ask you a question. How many of you have seen a plasma? So just put up your hands. Okay, well, a few hands going up, maybe about 2/3 of people. Well, for the other third, I'm going to say that actually you have seen a plasma, because there was one on my first slide. So you have seen one, but even if you didn't notice that one, there's another plasma that you should be familiar with. It's the sun. Okay, so if you haven't heard of this, then I'll be quite surprised. But it turns out the sun and all stars are just big balls of plasma. Okay, and the sun's a very hot, very dense plasma. So the stuff around the outside on the surface is about 6,000 degrees Celsius, and in the middle it's more like 15 million degrees Celsius. So it's pretty hot. Okay. So some of you may be surprised that the sun is actually a big ball of plasma out in space. So maybe some more things that you thought weren't plasmas actually are plasmas. So I've got another question for you. How much of the visible universe, that's the universe that we can see through telescopes and things, see directly, is a plasma? So how much of the visible universe do you think is a plasma? Okay, well I've got three options here. A is 0.1%. So anyone want to go for A, 0.1%? Okay, we've got a tentative hand going up here, very brave, thank you. B, 50%. That seems maybe more reasonable. Okay, yeah, a few hands at the back. Okay, so everyone else has read the advert for this talk, which I only realised today I'd written the answer in, but I'm glad some people were still caught out. So the answer is actually 99.9%. This might seem surprising to you. I mean, I'm not made out of a plasma, and no one else in the room is, so where is it all? Well, if we look out into the galaxy and into the universe, I actually see that quite a lot of what we thought maybe wasn't a plasma actually is. So this is a picture of the Eagle Nebula, and you might have heard this described as sort of gas, but actually it's not a gas at all, it's actually a plasma. The particles here are split up into the positive nuclei and the negative electrons. So nebulae are all made out of plasma. Well, in fact, a lot of the universe is made out of plasma. We already said that stars were plasma, and nebulae are plasma, and in fact even this dark stuff, this black space, which you probably thought was empty, actually has plasma in it. And there's not very much, there's very few particles. If you took a big meter cubed, you wouldn't find very many particles in it, so there's not very much there, but what is there is charged particles, and it behaves like a plasma. Okay, so the universe is filled with plasma, and the sun is a plasma. Well, isn't this a bit worrying, the big ball of plasma there, charged particles? Well, what's going on with the sun? We'll go back to the sun. Okay, so a big ball of plasma in the centre of our solar system. And you can see here that there's a big jet of plasma coming off. Okay? And this plasma is being thrown into space. And actually in the solar system, most of the empty space is filled with plasma. And again, there's not very much of it. If you took a centimetre cube at a random point in the solar system, you'd maybe expect to find one charged particle in there. That's it's a tiny box, but actually, remember how many atoms there were in me, so you'd expect a tiny box to have an awful lot of atoms in. Well, this plasma coming off the sun is what we call the solar wind. Okay, it's actually charged particles that are being thrown off of the sun by the energetic reactions that are going on inside. So I've got a video now, which I'm hoping is going to work, of the solar wind leaving the sun. And this disk in the middle, that's to block out the brightness of the sun, because otherwise it's quite difficult to see this. This bit around the edge is called the solar corona, and this video's sped up quite a lot, but you can see that every so often you get a big flare that pushes a lot more plasma out into space, and there's these constant ones always throwing material out as well. But just occasionally you get a big one. There we go. Okay, so let's follow some of this plasma through the solar system and see what happens to it. Well, I've got here a diagram of the plasma travelling through the solar system, and actually don't take this too seriously, it's a cartoon really of what's going on, and it's definitely not to scale. But anyway, we've got the sun here, and the plasma coming off, and this is a plasma wave going through space, so this is all charged particles going through the solar system, and this pale blue dot here is us. Okay? Now you might be wondering what these weird blue lines are, and I'm going to get to that now. So the blue lines are called magnetic field lines, and I know that sounds like a strange thing, a magnetic field. They're drawn on here, but you can't actually see the magnetic field lines, but we know they're there. There's a magnetic field being generated in the centre of the Earth, and this magnetic field is where I'm standing now, but it also permeates way out into space. Okay? And when these charged particles get to the magnetic field, they're forced to follow these lines. So that's what a magnetic field does. It tells charged particles how to move. And the force that's doing this is our old friend, the electromagnetic force. So when the charged particles reach Earth and hit the magnetic field, the electromagnetic force causes them to follow these lines. Okay, well, it might not obviously seem like it, but this is actually a really good thing for us, because we don't really want this plasma coming down to Earth and causing things like solar storms, which disrupt communications, and also it's just damaging for us. Some people believe that if it weren't for the protective magnetic field of the Earth, life would have never got going. And if we look to one of our nearest neighbours, Mars, that doesn't have a magnetic field, and it can't support an atmosphere, because its atmosphere is constantly being blown off by the solar wind. So it's a good job we've got this magnetic field deflecting all of the plasma from space, from our sun. But actually it doesn't deflect all of it, okay? So I've got this diagram here, and yeah, sorry, this is a bit complicated. There's lots of details on here which aren't really important. The important thing is that we've got our magnetic field lines again, and these red lines are the lines of some of the plasma coming from the sun. You can see that most of it actually just goes round and ends up here and goes past the Earth. But if you look at these two ones highlighted in yellow, you can see that some of it actually makes it to the Earth. Okay. So what happens is that this plasma is at really high energies, and it comes into the Earth's upper atmosphere. And when it goes into the Earth's atmosphere, it collides into particles in the atmosphere, particles like nitrogen and oxygen, which is what our atmosphere is mostly made up of. And when it hits those atoms, it excites them. And what I mean by excites is that the electrons in those atoms that get hit get a bit of energy. And they have this bit of energy, and they don't really want it. They want to get rid of it, basically. And they get rid of it by emitting some light. And this makes really pretty displays in the upper atmosphere. And at the South Pole, we call it the Aurora Australis, and at the North Pole, we call it the Aurora Borealis, or the Northern Lights. And I've got a picture here of the Aurora Borealis. This was taken in British Columbia in Canada. And it's a really beautiful display. And just think about what's happened here. Particles from the sun have travelled 150 million kilometres to the Earth. They've then collided at 1 million miles an hour with the upper atmosphere, excited the atoms, and then the atoms have re-emitted light. And this green stuff is actually oxygen emitting the light here. Okay, well, we've talked about plasmas in stars and in nebulae, and actually between stars as well. We talked about plasmas in the upper atmosphere colliding with oxygen and nitrogen. But these all seem a bit sort of spacey and far out, but there are some plasmas closer to home as well. So you all recognise this, it's just lightning. And actually lightning's a form of plasma as well. And there's some more examples. So yeah, you're probably thinking plasma TV. That's what most people think of when they think of plasma. And actually, you're absolutely right. Plasma televisions are plasma as well. And also neon strip lighting as well as a type of plasma. So we've found out a lot about what a plasma is, that it's made out of atoms that are split up into positive and negative charges. But we still don't know how they behave, even though we've seen loads of examples of plasmas. So what I'm going to do now is show you a plasma, and we'll see if we can work out a bit more how they actually behave. So this is a plasma globe, and what happens when I turn this on is an electric field is generated in the middle, and that causes the gas inside here to split apart into the positive and negative charges. Okay, so well, we can start asking how this behaves. The first thing is that it does look a bit like a gas, because it's just sort of filled the whole globe. I mean, it's not sloshing down in the bottom like a liquid would, and it hasn't condensed into a lump like a solid would. So it does seem more like a gas. But then if I put my hand on it, it doesn't seem very much like a gas at all, because gases, remember when we looked at them before and our volunteers were being a gas, they didn't care what other particles were doing. They were just happy to go off in straight lines, and they would only stop if they hit something else. But actually, plasmas aren't like that at all. If I put my hand on the plasma globe, it instantly changes its behaviour. And this is really unusual. No other state, if I filled this with water, it wouldn't automatically know that I'd put my hands on it. That makes plasmas quite different. Something else about plasmas, which is very difficult to show you today, is that they support all kinds of exciting waves that we don't see in other states of matter. they do support sound waves just like air does, but actually there's all kinds of weird and wonderful waves going on in plasmas. Alphen waves, Langmuir waves, they're all named after scientists. And there's also magnetosonic waves, which is sort of like a sound wave plus a magnetic wave. And you just don't see this behaviour in other types of matter. Okay, so we've seen that it's a bit like a gas, but actually not really, because it behaves as one. It doesn't really seem like a solid at all, and it doesn't seem to behave like a solid, but actually there is a similarity to a solid. Plasmas are a bit like metals in a certain way. Now you probably all know that metals conduct electricity. That's why we use them for making wires like this one out of. Inside this plastic is a piece of metal. And the reason that metals can conduct electricity is because they have some free electrons inside the solid. And those electrons can move around. And what electricity really is just charged particles moving around, flowing in a direction. Okay, well, if the charged particles in a metal mean that it conducts electricity, then obviously in a plasma, we should expect it to be able to conduct electricity as well, because all it's made out of is charged particles. And actually we saw that lightning was a plasma before, which should have given you a bit of a clue. But the charged particles in a plasma are actually much better conductors than the ones in a metal. Because in a metal, you've got the rigid structure, and a few electrons are free to go around, but they keep bumping into the fixed bits of the metal, and it slows them down. But actually, plasmas are fantastic conductors, because all of the particles are charged, and they're all able to move around one another. So plasmas actually make the best conductors, much better than metals. Okay, so inside a plasma, we've got electromagnetic forces acting on all the charges, pushing and pulling them in every direction. And we saw that when I put my hand on it, it changed instantly. Scientists call this collective behaviour, and it's one of the most interesting and different things about a plasma. No other state of matter really exhibits this sort of collective behaviour. No other state of matter has as many different types of wave as a plasma. So I talked about electric fields when I said I'd turn this on, and we haven't heard about electric fields yet. Earlier I talked about magnetic fields. And it's quite difficult to imagine, isn't it? You hear scientists say, oh, it's an electric field, oh, it's a magnetic field. You can't actually see it. Is it actually there? Well, I've got a demo to show that the electric field is there. So I've got this fluorescent light here. Now, I've not got a power supply on this. What I'm going to do is I'm going to hold it near the plasma globe, and you can see that even though it's not touching, you can come and have a look and check that I'm not touching against it. It's not even touching the glass. The electric field from the plasma globe is permeating the space around the globe. And when it goes through the fluorescent lighting tube, the atoms inside the fluorescent lighting tube lose their electrons as well. And actually we've got a second plasma in here. And this is actually how fluorescent lights work as well. So we found yet another plasma that's in your home that you maybe didn't know about. Okay, so we've learned a lot about plasmas. We've learned a bit about what they're made up of, atoms stripped into positive and negative charges. We've seen some examples of plasmas, and we've also had a look at how plasmas behave. They have complicated collective behaviour. So what are people like me actually doing with plasmas today? I mean, you know, what's the research on? What are we trying to understand and why? Well, I'm going to talk to you a bit now about the future of plasmas and the exciting research that's going on in the field. So this thing here is called an ion thruster. Okay, and it sounds like it's come out of science fiction, but I promise you people are actually building these things. And this is an example of a test ion thruster that was built by NASA. So ion thrusters throw out a little bit of plasma, and they use a lot of energy, but they don't use very much fuel. And they use electric and magnetic fields to propel this plasma out of the back. And this is perfect for travelling around in space. Because in space, there aren't very many fuel stations, but you can get a lot of energy from the sun. So NASA is looking at using these for moving around in space. One of the other applications of plasmas is in fighting cancer, and that's called hadron therapy, and I have some colleagues who are working on that. But what I'm working on, and what I think is actually the most important and most interesting application of plasmas in the future is something called nuclear fusion. So, I use that word nuclear, okay, which has some controversial connotations attached to it. So I'm just going to tell you how nuclear fusion differs from nuclear fission. So nuclear fission you've probably all heard of and are familiar with. Nuclear fission is what happens in power stations all over the world. It's been going for decades, and this is what the type of reactor was at Chernobyl and at Fukushima, and fission has problems. In fission, you take a really big, heavy atom and you split it up into some smaller bits. And when you split it up into these smaller bits, it releases a lot of energy. So that's how fission works. But it also releases some more of these bits here, which are called neutrons. And it's neutrons which set off the reaction going in the first place. So it's actually a chain reaction, which means that once you start it going, it's quite difficult to stop it again. So it just wants to keep making more atoms split apart and release more energy. This is one of the dangers of fission. Nuclear fusion, on the other hand, is quite different. In nuclear fusion, we take two piddly little atoms, sort of types of hydrogen, and we squeeze them together to make this new atom and this other bit here, a neutron. Okay? So it's a bit of a different process, and it releases even more energy than this process does. So it gives you lots of energy, but it isn't a chain reaction. It doesn't self-propagate. This thing doesn't go on and cause another reaction to happen because you need two of these. You don't end up with any of these. So the reaction just fizzles out if you stop putting energy in the form of heat in. Okay, and they're both called nuclear because they involve the nucleus, which we saw was in the middle of the atom. They both involve things changing to the nucleus, which is why we call it nuclear. But they're quite different things. Okay, well I said that fission was controversial. I'm sure you all know why. But what about fusion? What's fusion good for? Why should we be trying to make this happen in a reactor or a power station? Well, there are lots of things that get scientists excited about fusion, and I'm going to go through some of them now. And I know this is a lot of text, but I'm going to go through it all, and I'm going to tell you all how wonderful fusion is and why we should look forward to it working. Okay? Well, even if you really, really love fossil fuels, you just love burning them. You drive a huge car and you have your heating on all through the summer. Even if you love fossil fuels, eventually they are going to run out. And looking at the proven reserve, that is how many fossil fuels we've got at the moment, if we keep burning them at the current rate, they're going to run out in about 300 years. And I know none of us will be around in 300 years, but some of our grandchildren or great-grandchildren might be. So actually we want to get a new type of power source that isn't going to run out. Okay? Now you might be thinking about fission. Well, actually fission has the same problem. There's only so much of this uranium stuff, and we could make more complicated fission reactors that might last a bit longer, but with the current fission reactors, they're not going to last much longer than 300 years either. So what can we do? Well, renewables are often touted as the future, building wind turbines or solar energy, or hydroelectricity. But renewables have a problem. And don't get me wrong, I do love renewables. I think they're brilliant and they're a very neat solution. The problem is that they just don't create enough electricity. To create enough electricity with the current generation of renewables to power the UK, we'd have to cover the whole of Wales in solar panels or wind turbines. And personally, I just don't want to do that. I just think it's such a waste to throw away all that land. Most of the earth is covered in water, so it seems a bit callous to go around covering most of it in renewables. So the alternative then to covering large areas of land with renewables, or indeed large areas of the sea, is fusion. And as I said before, fusion releases an enormous amount of energy. It's the most energetic fuel that we have access to on Earth. Now there is a more energetic form of energy, but we don't have any of it on the Earth, so there's nothing we can do about it. So this means that we don't actually need to get very much of it to get a lot of energy out. So we don't need big mines and things. It's much easier to power. So I think I heard a statistic on the radio a couple of days ago that fusion could power the whole of London with just a few tanks full of petrol, with the same amount of fuel as is in a couple of cars worth of, the fuel tanks of a couple of cars could power London for a year. So you don't need very much of it. Fusion produces almost no carbon dioxide. I mean, it doesn't produce any directly, because we've actually got here, well, this is helium, which is fine, and this is a neutron, which I'll get to in a moment. It doesn't produce any carbon dioxide, so we don't need to worry about the greenhouse effect. The stuff that is produced is just from driving the fuel around and things like that, and we can work on that later. Now, the big problem with fission, of course, is radiation, and it is a problem with fusion as well, but it's a different sort of problem with fusion. The amount of radioactive waste generated by fusion is extremely minimal, and it's actually only inside the reactor chamber that you get any radiation. And it's also low-level radioactive waste, and that means that after 50 to 100 years, it's actually safe to handle again. Now, I know 50 to 100 years sounds like a long time, but in nuclear fission, we're talking about thousands of years for the most dangerous radioactive waste to become safe again. So in comparison, it's much better. And people are looking at ways to get rid of almost all of the radiation. And the radiation is really due to the fact that this neutron here comes off in the reaction, and that's bad because it can start radioactive processes going. But actually what we can do is we can take that neutron and absorb it in a metal called lithium and use it to generate more fuel. And that uses up the radiation and it usefully in making more fuel. So it doesn't have to be radioactive. Okay, and here's the real killer about fusion and what makes it really the choice for the future, okay? I mean, if we want the planet to continue to be powered and to continue using as much energy as we are, then we need to think about the long-term future. And there's enough fuel for fusion in seawater to last 1,000 years, okay? Now, that's a very basic form of fusion. If we got a more complicated, slightly more complicated version of it working, then we'd have enough fuel for 1 million years. And when that figure was calculated by David McKay at the University of Cambridge, that was based on us each using 100 times what the average American uses today, which, let me tell you, is a lot of energy. And it's also based on the population going up by a factor of 10, so about 70 billion people instead of 6 billion people. So fusion could last us for an extremely long time. Okay, so if it's so good, why hasn't anyone done it? Well, you're right to think that if you were. It's actually quite hard to get fusion to work. As I said before, it's not a chain reaction, so once you start it off, it doesn't keep going. It sort of fizzles out if you don't look after it. So are we barking up the wrong tree here? Is it ever going to work? Well, actually, there is a proven example of fusion working, and it's our old friend, the sun again. So the sun's actually just a big fusion reactor. It's a big ball of plasma in which those fusion reactions are happening all the time, and that's what powers the sun, and indirectly powers most of what goes on Earth. So the problem with achieving fusion on Earth is that the sun does it by using gravity to contain the plasma so that it doesn't all go spewing off, although you see that some of it still does escape. We haven't got the same mass as the sun. We're on a very much smaller, we don't have the same mass on the Earth. We've only got a tiny, tiny fraction of the mass. We can't use gravity. It's just not practical for fusion. So we have to use other methods. And because we don't have the same access to the same conditions in the sun, it's actually much more difficult to get fusion to work on Earth. It needs to be hotter. In fact, it needs to be 6 times hotter than the core of the sun to get fusion to work on Earth. So hotter than anything else in the solar system. It also has to be 100 times the density of lead. And lead's pretty solid stuff. And the pressure has to be 100 billion atmospheres. So that's 100 billion times more pressure than we feel walking around now. If you've ever been to the bottom of the swimming pool or done diving, you might have felt the pressure change. Well, imagine the pressure changing by 100 billion times. It wouldn't be very pleasant. So these are really extreme conditions, and it's so difficult to contain a plasma and make it behave. Some people have likened it to trying to confine a jelly with elastic bands. Every time you grab onto one bit, it flies off somewhere else. And you saw here earlier, I actually had a plasma in here, and it was confined, and it behaved well. although slightly strangely. But the plasmas for fusion are so much hotter that we can't just put it in glass because it would just melt the glass instantly. It's much too hot, much too dense to be contained by anything solid or liquid. So we have to use tricks. And there are two different ways of getting around this problem of holding the plasma. And one of them is called magnetic confinement fusion. So it's our old friend, the electromagnetic force at work here. Because plasmas are made out of charged particles, we can use the electromagnetic force to make sure it doesn't touch any of the walls. And I've got an example here. This is from the JET fusion reactor, which is in Oxfordshire. And you can see here, this is the inside of the reaction chamber. It's sort of like a big donut for reasons to do with the magnetic field. And here, actually, inset is a picture of the plasma in action. It might look like it's all sort of congregated on the walls and at the bottom of things. But actually, if you look carefully, it's being kept away from the walls. And that's actually the magnetic field stopping the charged particles getting too close. Okay, and on the right here, you can see some of the magnetic field lines, these things, a bit more clearly. Okay, and I've actually got a video of this to show you what it's like in action. So there we go, you can see that's the plasma. Sorry, this is in black and white. This isn't a white plasma. So you can just make out sometimes that, well, you can make out the sort of donut shape of the reactor and then the plasma being kept to these lines, and that's because of the magnetic field. Okay, well, this isn't actually the type of fusion that I work on. I work on something different, and it's called laser fusion. Okay, so this is quite a different approach. In magnetic confinement fusion, someone said, well, I know, we'll use a magnetic field and keep the plasma and we'll keep putting fuel into it and we'll keep it going. But laser fusion's a bit different. It's actually more of a sort of batch process. So we take a fuel capsule, and these are tiny, tiny fuel capsules. So this is actually about the size of the pupil in your eye. And we put it in this enormous target chamber. So this is a man that the fuel capsule goes in this tiny little gold box here, a big reaction chamber. And we actually use laser beams which come in at all sides and converge on this little box. And it's the laser beams which heat up the fuel in the capsule, turn it into a plasma, and then the fusion reactions happen really quickly. And it happens too quickly for the plasma to break up or lose its energy. So that's the way to get around it. You just do a little bit at a time, and you get it to react before it's really noticed. Okay, so we'll see a video of this now. And I'll just have to switch out a second to get this. Now there's some over-enthusiastic American narration on this, which I'm going to spare you. Okay, so the laser beams, by the way, are the most powerful laser beams in the world. And they're amplified many, many times to get them up to be extremely energetic. And I should really say that not only are they the most powerful in the world, but there's 48 of them. And each one of them is the most powerful laser beam in the world. So the engineering challenges for this are stupendous, but anything that hasn't been done already is just being invented as people go along. So for example, you need crystals to make laser beams. And before it took 2 years to grow the crystals, but they actually wanted to build this facility, which is out in the Californian desert, and get it working before then. So they invented a way to grow them in just 2 months. So that's the kind of mentality of the people working on this. They really want to get fusion to work. They want to get us off fossil fuels and have lots of clean energy. So these are the laser beams, and they've been amplified now, and they're split up into 192 beams from the 48. And they're heading towards the reaction chamber, which we saw a picture of earlier. And that's the reaction chamber just over there. They actually go much faster than this, just like I'd like to point that out. This is all happening in a fraction of a second. And the power used by this facility is actually 14 times that of the UK national grid. So at the moment, it's a bit of a problem getting more energy out than in, and that's really what is going to prove fusion when someone demonstrates that you can get more energy out than in. So now the laser's been converted into ultraviolet laser, and then it converges on this tiny, tiny gold box. And inside the gold box, we have our fuel capsule. Now the lasers hit the gold box, and the gold actually turns the laser light into X-rays. And X-rays are actually better for getting an even bathing of the fuel capsule. So it hits each part of the fuel capsule equally, and that helps us squash it down to a tiny point. So now it's a plasma, and the fusion reactions have started happening, and there we go. So that So that is the version of fusion that I'm working on. And my actual PhD is on the bit where the X-rays had got into the fuel capsule and they turned it into a plasma, and then the fusion reactions had started to happen. Because really we want as much of that fuel inside that fuel capsule to fuse as possible. And if it does all fuse, then that is going to give us more energy out than we put in. And at the moment, not very much of it actually fuses. So what I'm doing is trying to work out how we can get more of the fuel to actually be used up. Okay? Well, I hope you've all enjoyed hearing about the mysterious fourth state of matter, and you've appreciated a little of why it is mysterious. We talked at the beginning about matter being made up of atoms, and we talked about turning the temperature up on some matter and seeing what the atoms did. We found out that a plasma is actually made up of charged particles. It's when the atoms split up into negative electrons and positive ions. We saw some examples of plasmas. We saw that plasmas were in stars, between stars, in the nebulae, in lightning, in your front room. They're everywhere, and they're really important. And we actually saw that plasmas make up most of the universe. And the most important thing for me about plasmas was the fact that they could be the key to fusion. Thank you all very much for listening, and I'll take any questions that anyone has.